Well, the first thing I have to tell you is that you probably have some picture in your head about what antimatter is. And it is probably not quite right. Most people think antimatter is just regular matter with something flipped around, like a mirror image. And that is sort of true, but it misses the really interesting part. You see, the story of antimatter is one of the most beautiful stories in all of physics, because antimatter was not discovered by someone going into a laboratory and finding something strange. No, no, no. It was discovered by a man sitting at his desk, staring at equations, and finding something that should not be there. Here is what happened. There was a physicist named Dirac, very brilliant fellow, and he was trying to write down the correct equations for how electrons behave. Now, this was in the late 1920s, and people already knew about quantum mechanics, and they knew about relativity, and Dirac wanted to put them together. He wanted an equation that respected both. So he worked, and he found the simplest possible equation he could write down. Beautiful equation, very elegant. And it worked wonderfully for describing electrons. But there was a problem. The equation had solutions that made no sense. There were solutions with negative energy. Now, what does that even mean? An electron with negative energy? It sounds like nonsense. And most people would have thrown those solutions away and said, well, the math gives us some garbage, we just ignore the garbage. But Dirac did not do that. Dirac took the crazy answer seriously. He asked, what if these solutions are trying to tell us something? What if nature actually uses these strange solutions? And he made a prediction. He said there must exist a particle that nobody has ever seen before. A particle exactly like the electron. Same mass, same everything, but with the opposite electrical charge. The electron is negative, this new particle would be positive. He called it the anti-electron. We call it the positron now. And you know what? A few years later, a fellow named Anderson was doing experiments with cosmic rays, you know, particles that come raining down from outer space, and he found it. He found a particle that curved the wrong way in a magnetic field. It had the mass of an electron, but it curved like it had a positive charge. The positron was real. Dirac predicted it from pure mathematics, and there it was. Now, this opens up a whole question. If the electron has an antiparticle, what about the other particles? What about the proton? What about the neutron? And here people get confused. They say, fine, the antiproton has the opposite charge. The proton is positive, the antiproton is negative. I can understand that. But then they ask about the neutron, and they say, wait a minute, the neutron is neutral. It has no charge. So how can it have an antiparticle? What is the opposite of nothing? And the answer is very interesting. The rule of the anti is not just that it has the opposite charge. That is what everybody thinks, and it is not quite right. The antiparticle has a whole set of properties that are opposite. There are other characteristics that particles carry besides electrical charge. And when you flip all of those, you get the antiparticle. So yes, there is an anti-neutron. And the difference is easy to see. You put two neutrons together, nothing special happens. They just stay there being two neutrons. But you put a neutron and an anti-neutron together, they annihilate each other. Big explosion of energy, gamma rays, mesons, all kinds of things come flying out. Now, when matter meets antimatter, they do not just react like chemicals mixing together. They annihilate. The particles destroy each other completely. All of their mass, 100% of it, converts directly into energy, into light. Think about that. When you burn wood, a tiny fraction of the mass becomes energy. Most of the stuff is still there as ash and smoke. When a nuclear reaction happens, maybe 1% of the mass becomes energy. But matter and antimatter, everything, the whole thing, gone, transformed into pure light. And this is not some theoretical idea. This happens in laboratories. You can make positrons. You can see them. You can watch them curve the wrong way between metal plates. And then you watch a positron bump into an electron, and both of them disappear. Two gamma rays come out, carrying all the energy that used to be the mass of those two particles. It is directly observed, easily, in the laboratory. Now, let me tell you how we really think about this, because so far everything sounds reasonable, strange, but reasonable. Opposite particles that annihilate when they meet. Fine. But there is a deeper way to understand what a positron actually is. And it comes from looking carefully at the mathematics. When we calculate what happens with electrons, we draw little diagrams, pictures. Space goes one direction, time goes another direction. Usually we put time going upward. And we draw lines to represent particles moving through space and time. Now there is a mathematical function that tells us the amplitude for an electron to go from one point to another. Let us call 1.5 and another 0.6. The function tells us the amplitude for the electron to go from 0.5 to 0.6. If 0.6 is later in time than 0.5, everything is normal. The electron goes forward in time. That is what we expect. But what if 0.6 is earlier than 0.5? You would hope the mathematics give 0. You would hope there is no amplitude for an electron to go backward in time. That would be sensible. That would be comfortable. But it is not 0. The mathematics says there is an amplitude for this. And when you look at what this backward going section is like, something very interesting happens. You see, the electron carries a charge, and we put arrows on the lines to remember which way it is going. Normally, the arrow points forward in time, but in this case, the arrow is going the wrong way. And this section going backward in time, it has almost all the same properties as an electron. Same mass, same interactions with light, but it curves the wrong way in a magnetic field. It behaves like it has a positive charge. It is just like an electron, except it is positively charged. It is called a positron, and it really exists. So you see, a positron is not just some separate particle that happens to be opposite to an electron. From this way of looking at it, a positron is what an electron looks like when it is going backward in time. Now let me show you what this means. Imagine an electron moving along through space and time, going forward, doing its thing. Then at some point, it interacts with light, with photons, and something happens. It starts going backward in time. That section going backward, it looks to us like a positron going forward, because we see time flowing in one direction. Then later, this backward going section interacts with more light and turns around again. Now it is going forward in time, looking like an electron again. What do we see? We are sitting here watching time go forward like sensible people. What do we observe? We see light come in, and suddenly two particles appear that were not there before, an electron and a positron. They exist for a while. Then they come together, annihilate each other, and produce light again. But from the mathematics, there is really just one line, going forward, then backward, then forward. Now I want to be very clear about something. This is not philosophy. This is not just a way of talking about it. This is how the calculations actually work. When you compute probabilities using this picture, you get exactly the right answers. The experiments confirm it. So it turns out that for every particle in nature, there is an antiparticle, and they are connected through this mathematics of going forward and backward in time. Antiprotons exist, and a proton and an antiproton can come together and annihilate each other, just like the electron and positron. Now here is something practical. When a positron is actually made in the laboratory on Earth, it does not go very far before it disappears. Why? Because the world is full of electrons. The walls are made of atoms, and atoms have electrons in them. So the positron wanders around, bumps into an electron, and they annihilate. Gone. 2 gamma rays come out. But if you are clever, you can keep them. You can make positrons go around in a circle using a magnetic field. Keep them away from the walls. Do not let them touch any electrons. And they stay. They stay, and they stay, and they stay. For days, going around in a circle,
untouched by human hands. In fact, we do experiments by speeding up positrons going around in a circle to very high energy and making electrons go in a circle in the opposite direction. And we look at what happens when they collide with each other. New particles come out. It is one way we discover things. So there is nothing different about a positron than an electron. They are completely symmetrical, same mass, same behavior, except for history, except for the fact that our laboratory, our world, has a lot more electrons than positrons. We have an excess of electrons. Why? Nobody knows. Now let me tell you more about what actually happens when matter and antimatter meet, because this annihilation business is very interesting. When an electron and a positron come together, they annihilate and produce two photons, two gamma rays, light. And these gamma rays carry away all the energy that used to be the mass of the electron and the positron. But the reverse also happens, and this is very important. If you have a photon with enough energy, it can turn into an electron and a positron, a pair. Out of light, you get matter and antimatter. Think about what this means. Energy can become matter. And not just any matter, it becomes matter and antimatter together, always in pairs. You cannot make an electron without also making a positron. They come together. This is called pair creation. And it happens all the time. Cosmic rays come down from space, hit atoms in the atmosphere, and create pairs of electrons and positrons. In laboratories, we shoot high-energy photons at targets, and pairs come out. So you see, the universe has this rule. You can convert energy into matter, but you must make equal amounts of matter and antimatter. And you can convert matter back into energy, but only by bringing matter and antimatter together. Now let me tell you how we draw pictures of all this, because the pictures are very useful for understanding what is happening. We draw diagrams. Space goes one way, time goes another way, usually upward. An electron moving through time is a line going up. A positron, which is an electron going backward in time, is a line going down. And a photon, a particle of light, we draw as a wavy line. Now, when an electron and a positron annihilate, what does the diagram look like? You have a line coming up. That is the electron going forward in time. You have a line coming down. That is the positron, which is really an electron going backward in time. They meet at a point, and from that point, wavy lines come out, the photons. But here is the thing. From the diagram, you can see that it is really just one line. The electron comes up, reaches the point, and then goes back down. What we call the positron is the same line, just going the other direction in time. And at the point where it turns around, light is emitted or absorbed, depending on how you look at it. Now, the reverse process, pair creation. A photon comes in, and an electron and positron come out. In the diagram, you have a wavy line coming in, and from a point, two lines come out. One going up, the electron, one going down, the positron. But again, from the diagram, it is really one line. The electron going up, then turning around and going down, which looks like a positron going up. So all these processes, annihilation, pair creation, they are all connected. They are all the same thing looked at from different angles. It is just electrons interacting with light and sometimes going forward in time, sometimes going backward. And the calculations work. When you compute the probabilities for all these processes using these diagrams, you get the right answers. The experiments confirm it. Now, I told you that when a positron is made on Earth, it does not last long because there are electrons everywhere. But there are ways to study them. In the laboratory, we can make beams of positrons. We speed them up using electric fields. We bend them using magnetic fields. And we can see that they bend the opposite way from electrons. Same mass, opposite charge, just as the theory predicts. And we can do something very interesting. We can take positrons and electrons and make them go around in circles in opposite directions, very fast, near the speed of light, and then we make them collide with each other. What happens? They annihilate. But because they have so much energy, the photons that come out can immediately create new pairs. Not just electrons and positrons, but other particles too. Heavier particles. Particles we would never see otherwise. This is one of the ways we discover new things about nature. We smash electrons and positrons together and see what comes out. It is like taking two simple things, colliding them, and finding out what the universe is made of at a deeper level. And it all comes from this idea that positrons exist, that they are electrons going backward in time, that matter and antimatter can annihilate into energy, and energy can create matter and antimatter. Now, if we have anti-electrons, anti-protons, and anti-neutrons, we can, in principle, make anti-atoms. Think about hydrogen. One proton in the center, positive charge. One electron around it, negative charge. They attract. Very simple. Anti-hydrogen would be one anti-proton in the center, negative charge. One positron around it, positive charge. They attract too. Same masses, same forces. Everything works the same. An anti-hydrogen atom would emit the same colors of light as regular hydrogen. Exactly the same. You could not tell the difference just by looking at the light. If you made a whole world out of antimatter, it would work exactly the same as our world. Anti-chemistry would be the same as chemistry. Anti-biology would be the same as biology. Anti-people would live their lives and never know they were made of the opposite stuff, unless they tried to touch something made of regular matter. Then, annihilation. Now this raises a very big question. If matter and antimatter are so symmetrical, if they behave exactly the same way, then when the universe began, there should have been equal amounts of both. But look around. The Earth is made of matter. The sun is made of matter. The stars, the galaxies, everything we can see, matter. Where is the antimatter? Some people thought maybe there are regions of the universe made of antimatter, anti-galaxies far away, and we just cannot tell because the light they emit looks exactly the same. But there is a problem. Where matter and antimatter regions would meet, there should be annihilation, lots of it, gamma rays everywhere. We should see this. We look at the sky with gamma ray telescopes, and we do not see the signature of matter and antimatter annihilating at the boundaries. So it seems the universe is almost all matter. The antimatter is missing. Why? How did this happen? If the laws are symmetrical, if every process that makes matter also makes antimatter, how did we end up with more matter? There must be some slight asymmetry, some tiny difference in the laws that we do not fully understand, something that made a little more matter than antimatter in the very beginning. And then what happened? All the antimatter found matter to annihilate with. Almost everything was destroyed, turned into light, but there was a little bit of matter left over, that tiny excess, and that is us. That is everything. We are the leftovers. Everything you see, every star, every planet, every person, we are the small residue that survived the great annihilation at the beginning of the universe. What is that asymmetry? Where does it come from? Nobody knows. This is one of the big unsolved problems. You know, this is how physics is. You discover something beautiful. Antimatter exists. Positrons are electrons going backward in time. Matter and energy can convert into each other. Wonderful. And then you find something you cannot explain. Why is there more matter than antimatter? The universe does not tell us. Not yet. But we keep looking. We do experiments. We smash particles together and see what comes out. We look at the sky. We write equations and see what they predict. And maybe someday somebody will figure it out. Maybe some young person will see something we all missed. That is how it works. That is science. What we know is already remarkable. That there is such a thing as antimatter. That it was predicted from pure mathematics before anyone ever saw it. That every particle has an antiparticle. That you can create matter from energy and turn matter back into energy, and that somehow, against all expectations, the universe ended up with more stuff than anti-stuff. And here we are, made of that stuff, trying to understand how it all works.